Welcome to Spring LIB.
In this exercise, we have a cylinder that has a mass of 4 kilograms and is supported by a spring that has a stiffness, Kab, that is equal to 120 newtons per meter. And the system is initially at the equilibrium position. That is, the spring is neither moving up nor down, that is, the cylinder is neither moving up nor down, when a certain force F that is equal to 60 newtons starts acting on the system downwards as shown in the figure. Our goal is to find what is the speed of the cylinder after it moved a distance s equal to 0.2 meters from the equilibrium position. And in order to solve this, we need first to remember how we deal with the elastic force. So remember that the force caused by a spring is equal to minus K is the stiffness, times the displacement of the spring. The minus is here to show that the force is opposite to the displacement of the spring. So in our case, the spring is compressed, so the displacement is pointing downwards, meaning that the force, so this is delta x, the force F will be pointing upwards. And its magnitude is kx. Okay, so in order to find V, we also need one more information besides the elastic force. We also need to find a relation between the speed V, the acceleration, and the displacement x. Okay, so basically I'm just going to start with the identity that A is equal to dv dt, and I'm going to multiply both sides by V. So we have A times V is equal to dv dt times V. So we have that A times V, which is just dx dt, is equal to dv dt times V. So the dt's cancel out, and we're left with V dv is equal to A dx. So we can integrate both sides, and we get a relation between the acceleration, the speed, and x. So now we are able to dive into the exercise. So what we have is a cylinder. This one here, it's just seen from the side. And I'm going to draw a free body diagram on the cylinder. So we have the elastic force that points upwards. So I'm going to call it Fk. We have the gravitational force that points downwards, and that is just mg. And we also have the force F that is equal to 60 newtons that acts downward. Now Fk, the magnitude of Fk, is Kab times the equilibrium position, which I'm going to call x0, plus the displacement x. Now the equilibrium position is the position when Fk is equal to mg. That is, that's the initial position before the force F acts on the system, when the gravitational force perfectly compensates the elastic force. So we have Kb x0 is equal to mg. So x0 is mg divided by kab. Now m is 4 kilograms. G is 9.8 meters per second squared divided by kab, which is 120 newtons per meter. So x0 is equal to 0.327 meters. Okay, so this is the equilibrium position. And we have, so basically what we have is that Fk is equal to K A B, that's the stiffness, times 0.327 meters plus S. So, and the free body diagram that we drew up here, tells us that the sum of the forces, that is the net force, is equal to Fk, so that's Kab, times 0.327 meters plus S minus mg minus the force F is equal to the mass times the acceleration. So the acceleration is Kab divided by the mass times 0.327 meters plus S plus minus G minus F. Now Kab is 120 Newton per meter. We have to divide it by 4 kilograms and multiply it by 0.327 meters plus S minus G, that's 9.8 meters per second squared, minus F, that's 60 newtons. So we have that A is equal to 9.8 meters per second squared plus 30 times S. This is in meters per second squared as well. Actually, I'm going to just leave the unit implicit because it's always meters per second squared. So let me write it as 9.8 plus 30S minus 9.8. And actually, the 60 here should have been divided by 4 kilograms. I'm sorry for that. Minus 15 kilograms. Okay. So this is equal to 30S minus, actually not 15 kilograms. Sorry for that again. It's 15 meters per second squared. So minus 15. Now notice that this is the value of the acceleration. But notice that as the force F, I'm sorry, let me write it here. We have that the force F is pointing downwards. And initially that'll cause the system to be accelerating downwards. So actually the acceleration is negative. So this means that the absolute value of the acceleration is equal to 15 minus 30s. Okay. Okay, this is the absolute value of the acceleration. Now we can apply this to the equation that we had before. We had that the integral from of v dv is equal to the integral of the acceleration. So I'm going to use the absolute value of the acceleration. times dx. Now notice that x is equal to x0 plus s, so dx is equal to ds. Okay, so basically we have the integral of v from 0 to v, since the initial speed is 0 when the spring is in equilibrium, of the integral from s equals 0 to s equals 0.2 meters of 15 minus 30 s ds. The first term results in v squared over 2, and the second term is 15s minus 15s squared from 0 to 0.2 meters. So this is equal to 15, actually let me write it like this. V is equal to the square root of 2 times 15 times s, which is 0.2 minus s squared, which is 0.2 squared. So v is equal to 2.2 meters per second. So this is the speed of the spring as it passes through the point s equals 0.2, which concludes our exercise.